Today we're talking about absolute value inequalities. So when we're looking at basic absolute value inequalities, if we have a positive number k, we can make four different inequalities involving the absolute value of x and k. Absolute value of x is less than k, is greater than k, is less than or equal to k, or is greater than or equal to k. We want to graph the solution sets to these four different inequalities. So let's start by looking at the first one. The absolute value of x is less than k. Well, x could be a positive or a negative number. When we take the absolute value of it, of course, we're going to get something positive, but x itself could be positive or negative. If x is positive, then it would have to be between 0 and k because, well, it would be positive and it would be less than k. If x is negative, in order to get something whose absolute value is between 0 and k, you would have to have something that's between 0 and negative k in this interval here. So all of the possible solutions of this inequality lie in this interval right here. Notice that we do not include these endpoints because this is a strictly less than. If we look at the next inequality, that is less than or equal to, the graph is very similar, but it does include those endpoints. So remember that the open circle on your endpoint indicates it goes right up to k but does not include that actual number, whereas here we go right up and including k. So now when we look at the absolute value of x is greater than k, well, if x is positive, then x would have to be greater than k, which puts it in this interval here, anywhere to the right of k. So if x is negative, if x is in this interval, when we take the absolute value of it, we'd end up here, which would be less than k. So in order to get something whose absolute value would be greater than k, you have to go on the left side of negative k. And so for the solution set here, we have two disjoint pieces. Two disjoint pieces that are unbounded intervals each. And again, we have open dots on our endpoints because this is a strict inequality. When we are talking about greater than or equal to, we will have a similar graph, but one that includes these endpoints. So next, let's put our solutions in interval notation. This is an interval between negative k and k. It does not include the endpoints, so it's an open interval. Remember, we use parentheses for an open interval. And similarly, except we do include these endpoints, so this is a closed interval. Here we have two different pieces, so we have to talk about this as the union of two different intervals. So we've got negative infinity to negative k, and then also k to infinity. And we join those with the union sign. That gives us that entire solution set. And of course, notice that we are not including k for our strict inequality. Down here, where we do include the or equal to, we do include k and negative k in that solution set. This is an alternative graphing style. It represents the same thing. Here we have parentheses-like and marks to our endpoints. Instead of the open circle, they are reminiscent of the parentheses that are on the actual interval. You can use square brackets too. This is just a different graphing style. The previous graphing style here is kind of nice because it generalizes better to two dimensions, but this one is fairly common, and in fact our textbook uses it, so I will require you to be able to go back and forth to know both the open dot and closed dot notation as well as the parenthesis and square bracket notation. So now we'll look at these same inequalities from a different perspective. We want to rewrite each of these absolute value inequalities as a compound inequality, which means we can use more than one inequality symbol, and we won't be using any absolute value signs. We'll start again with the absolute value of x is less than k. So this is the solution set to this inequality. It's the interval between negative k and k, which means x has to be greater than negative k, and also it has to be less than k. We could write that with the word and, or we can write it as a connected compound inequality like this. Of course, this one is similar. We do have the less than or equal to symbol here, so we will have that in our answer as well. Now over here, where we have two disjoint intervals, we have to express it as two disjoint pieces. Either x is going to be less than negative k, or it's going to be greater than k. And our final one is similar, except of course we have a greater than or equal sign, so it's either less than or equal to negative k, or greater than or equal to k. These are going to be useful. We can use them to rewrite other absolute value inequalities and find their solution sets. So here we want to solve the absolute value of 2x minus 1 is greater than 15. So notice that we have the absolute value of something is greater than a number, which means we can rewrite it as one of our compound inequalities. Either this thing inside the absolute value sign is less than negative 15, or this is greater than 15. So we can split it up like that. Now we have two simple linear inequalities that we can solve one at a time. First we'll start with, the first one. And we just go through the process, and x is less than negative 7. Then we still have this. We can't forget about our second inequality. So we have two inequalities that tell us the solution set. These first two were connected with an or, so x is less than negative 7 or x is greater than 8, which gives us an interval notation, the interval from negative infinity to negative 7, union 8 to infinity. And there it is as a graph. So back to our basic absolute value inequalities. These were the ones between the absolute value of x and k. Very simple inequality. What if now we suppose that k is a negative number? The absolute value of x is always non-negative. It might be 0, it might be positive, but it can't be negative. If we're comparing it to a negative, we can just reason out the answer. If we have the absolute value of x is less than or equal to k, and again here k is a negative number, well, it can't ever happen that this is less than or equal to k. So our answer there would be no solution. Over here, if the absolute value of x is greater than or equal to k, and again here k is a negative number, well, a positive number or 0 is always going to be greater than a negative number. So the answer to that would be all real numbers. If you wanted to put this in interval notation, you can use the negative infinity to infinity. Over here, you can't express no solution as an interval, but you can use the empty set symbol. And these things also hold for the strict inequalities, not just the less than or equal to. And that concludes our lesson on absolute value inequalities.